1 mole of naphthalene, C10H8, and the molar mass of naphthalene is 128.08 grams per mole, times the density of naphthalene. If you were to guesstimate a density, what would you guesstimate? Just come up with a guess. Naphthalene. Have you ever heard of naphthalene? Naphthalene they use in like mothballs. Keep moths away. 1.14. It's not very dense stuff. It's slightly more dense than water. 1.14 grams per cubic centimeter. The reason I'm writing this is because I don't want to make the assumption before seeing enough examples that the assumption does work. Somebody might tell you, right? The problem is somebody might tell you, okay, let's go ahead and always assume this, But the problem is, if you get in the habit of doing this, then eventually in your scientific career, somebody's going to call you on that and say, well, really, how good is that assumption? What kind of percent error am I introducing by using this particular assumption? And then if you just sit there, especially if you're getting, let's say, your PhD or something like that, and you've always assumed this because somebody has always told you to assume this, it doesn't look very good. Actually, I've seen that happen a bunch of times when people, use that. Well, after you kind of justify this, then let's go ahead and assume we can ignore solids and liquids. And so I'll let you calculate the volume on your own here. Plus 12 moles of gas, etc. And so once we calculate, we calculate the delta V. We'll plug that in here. The pressure is just going to be 1 atmosphere. Then we're going to convert this into joules or kilojoules. And then we just plug it in here. And we're done. It turns out that when you do this calculation, the work amounts are quite a bit smaller, than the heat. And so the work, yesterday I was drawing a small arrow for work and a big arrow for heat. That's typical because the work is, you're usually looking at 100 joules for a liter of expansion. And so if you had, let's say, 50 liters of expansion, that's only 500 joules, which is just a half a kilojoule. A half a kilojoule for 50 liter expansion, well, a half a kilojoule for 50 liter expansion doesn't even make an impact on this. A little, but not much. And so the work terms are typically small. You'd have to have a huge expansion in order for something to make a big impact on a kilojoule. Here. So I'll let you finish this calculation here. Okay, now that's comparing delta U and delta H. Well, delta H for us is going to be much more useful than delta U. And so let's focus on delta H, because delta H is what? Here. This work, actually, was this work done by the system or done by the surroundings? Done by the surroundings. So that means, this heat output that we get is actually greater than the heat output we would have expected using delta U. The amount of energy that we get from doing this under constant pressure is greater because the work, delta V is going to be negative, right? Is that correct? Delta V is negative because we're losing. So delta V is negative. Negative times negative makes this positive. And so delta U, do you see delta U is going to be less because this is positive, this is negative. So we're going to get less heat output in the surroundings. If we get less heat output, well, then this is better because, you know, when we do this under constant pressure, we don't use delta E. Just delta, we don't use delta U. We're going to use delta H because most, like 95% of the reactions we do, 99% of the reactions we do are constant pressure. So delta H is very useful because this is the net. Now, what can I do with this? This is the net energy. Well, you know, this net energy is the usable energy. I couldn't use this, you know, this energy from the, well, actually I can because the surroundings are doing it. But this is the usable energy. Now, this energy doesn't have to be heat. You know, they just call it the heat of reaction because that's what it is, traditionally known. But this can be used to do work also, you know. This energy, you know, when you burn something, you just don't have to heat a pot of water. When you burn something, you can do mechanical work as well. And so how much work can you get out of that? Well, in theory, we could get out this much. If we can convert all this energy into work, then we can get this much work. But unfortunately, machines aren't that efficient. And so machines, you're going to have some loss, you know, frictional loss or whatever else due to heat. And so, for example, when we burn gasoline, you know, gasoline, we're going to have a heat of combustion of gasoline. Is all that converted into heat? You know, all those kilojoules converted straight into, no, a lot of those kilojoules are converted into work. Now, for some of you in physics, a lot of people get confused with something like the Carnot cycle. You know, but the Carnot cycle, has anybody heard of that? Carnot cycle? The confusion comes because this is not heat. This is potential energy. And so what we're doing is we're converting potential energy into usable energy. We could convert it into heat, or we could convert it into work. That's potential energy. If this were all output as heat, then we have some restrictions with the Carnot. Converting heat into work is a very inefficient process, but we're converting potential energy into usable energy, which it could be either used as heat or work. And so, you know, I got into one of my students was complaining to me that you're wrong, you know, it's impossible to convert that into work with, you know, greater than this efficiency. Well, they were thinking in terms of heat, but well, I was thinking in terms of potential energy. It's different. And so, anyway, we don't just, you know, when you burn gasoline in a car, it doesn't convert it into heat and then take that heat and convert it into work, right? That's like nuclear reactors are terribly inefficient because that's what they do. They convert all that energy into heat up water, generate steam, right? And do that. But we're doing something else. In fact, you know, we could convert a lot of these. You know, these are redox reactions. We can convert a lot of these into electricity, you know. And so when you're looking at a hydrogen fuel cell or methane fuel cell car, which converts these combustion reactions into electricity, there's no combustion, there's no flame. It's converting all that potential energy, not into a flame and not into heat, it's converting it into electricity. Okay. Obviously, there's going to be heat produced because it's not 100% efficient. But there. Well, let's go on with that. And so I'll let you finish this calculation here as well. And so what we're interested in is delta H. And so the second part of this chapter just deals with delta H. And so let's take a look at delta H. Delta H is going to be extremely useful, but the delta H calculations aren't difficult. And so delta H is extremely useful and so let's take a look at a delta H calculation, and then we're going to look at how do we get delta H's. So let's go to advanced integrated here. We're going to look at this one here, 107. metabolism of glucose. The metabolism of glucose, C6H12O6, which is a carbohydrate, yields CO2 and water as products. Heat released in the process is converted to useful work with about 70% efficiency. So we're going to take that potential energy and convert that potential energy change, because is there any kinetic energy change in this? No. So we're converting that potential energy change into about 70% work and 30% heat. 70% efficiency. Calculate the mass of glucose metabolized by a 58.0 kilogram person in climbing a mountain with an elevation gain of 1,450 meters. Assume that the work performed in the climb is about 4 times that required to simply lift a 58.0 kilogram mass by 1,450 meters. They give us delta H of formation like this. Okay, and so we're going to use the energy from metabolism of glucose to climb the mountain. So how many grams of glucose do we need to consume to climb that mountain? And so here, glucose metabolism, C6H12O6 solid plus SO2 gas, CO2 gas plus 6H2O liquid. And we want to figure out what delta H for this is. Delta H for this reaction. All right, what are all the ways I can figure out delta H? And so what are the ways I can determine what delta H is? Probably one of the most direct ways of determining delta H is what you did in experiment 2, which is what? You did in experiment 2 to determine delta H. You did constant pressure, calorimetry. And so if we get QP, yeah, then we can do it. How do we get QP? We do constant pressure calorimetry. And so we burn this, we burn it. You probably don't want to use a styrofoam cup, but you burn it in a cup or something in the open lab and figure out how much heat's released. You got to capture that heat some way. But constant pressure calorimetry for combustion reactions is inconvenient because it's hard, to contain that combustion reaction. But anyway, this would be the most direct because delta H is just equal to the QP divided by the amount in moles. And so that's one way we could get delta H. So we do calorimetry. Probably much more convenient is we do a QV, because if you burn it in a bomb, it's much easier to contain all the heat. And so we burn it in the bomb, but if we burn it in the bomb, we don't get delta H. What do we get? We get delta U. So we get delta U, and then what we have to do is we have to do a thought experiment. What is the thought experiment? Well, we get delta U because we just take QV divided by the amount. And this is why I do everything by the mole, because delta U and delta H are always normalized per mole, And so it's much easier to think per mole here rather than this per gram over here, however many grams I burn. I'm not going to burn a whole mole of it, right? I'm just going to burn a little bit. All right, now what we do is we do this under constant volume, but then we do a thought experiment where we shift universes and we transport ourselves to the constant pressure universe. And imagine we're burning a full mole of this under constant pressure conditions, right? And then we do that, and then we just calculate the work involved in this, because delta H is just equal to delta U minus the work. And so we just calculate the work if we did it, if done at constant pressure. We aren't actually doing it at constant pressure, but we can figure out how much work would be required just from the calculations I set up earlier. It's not a difficult calculation, V initial and V final. Especially if you ignore solids and liquids, then it's even easier because you're just looking at gases. The volumes of gases are very easy to calculate, right? And so here, and then we get our delta H here. But the problem is both of these require calorimetry experiments. Calorimetry experiments are a pain. And so is there a way to do it without doing calorimetry? And there is a way of doing this without doing calorimetry. And it's called Hess's law. So let me talk about Hess's law. Yeah. Hess's law says that if you know delta H for reaction 1, let's say we have delta H for that, we'll call it delta H1, and we know delta H for reaction 2, delta H2. If we can add these 2 or more, you can add a whole bunch of these, then we get the net reaction. Let's say that's reaction 3. Well, that's delta H of 3 is just equal to delta H1 plus delta H2. And so what we have here is this, that net reaction is just going to be the sum of the reactions that we just added up here. This is Hess's law. And so that means this, if I can figure out 2 reactions that I can add up to get this net reaction, 2 or more, in your homework you're going to have like 5 reactions you might have to add up to get the net reaction here. And then we figure out a way to add those up, then we're okay. But Hess's law, we require a few other things too. And that is, if we reverse the reaction, if we reverse the reaction, then we take the negative of the delta H of the forward reaction. The negative of the delta H of the forward reaction is equal to the delta H of the reverse reaction. And so we just change the sign. So let's say if it costs you 1,000 kilojoules going up, then you're going to get 1,000 kilojoules going down. This is because of the first law of thermodynamics. Right? If you multiply by some n value, it doesn't have to be an integer, just any number, times the reaction 1, then what you're going to see is you're going to get n times delta H1. And so n could be a fraction. For example, if you multiply by half, then you're going to get half as much energy. So if you burn half a mole rather than a full mole, obviously you're going to get half as much energy. If you burn 2 moles rather than 1 mole, you're going to get twice as much energy. And so energy is an extensive property, and so this is what we have here. And so using these 2 things, we can manipulate the equations we add, because sometimes the delta H's we have are reversed, not exactly what we want. And so, common things, this is an example of Hess's law here. Hess's law is, but this is using energy level diagrams. It's a pain in the butt to use energy level diagrams like this to figure out Hess's law. It's much easier just to take the reactions and just add them up. And so, typical Hess's law problem. Actually, did you guys do Hess's law in Chem 4? No? Okay. That's a surprise. Typical Hess's law problem, they give you a whole bunch of data. Here's reaction 1, reaction 2, reaction 3, here's the desired reaction. So you've got to figure out a way to add these up. And so here we have C3H4 gas, 1 mole. Well, this already has C3H4 gas, 1 mole, so we use this equation as is. I wouldn't change that. Here we have 2 H2s. Well, we need 2 H2s. Here we have 1 H2. So I double this equation, I get 2 H2s. Ignore everything else. Here we have C3H8, and so using these, we didn't have it. Oh, here, C3H8. Here's C3H8, but it's on the wrong side, so I reverse this and double it. And then add them up. And this should add up to the net reaction. I'm done. Everything else should cancel out. So that's why I ignore everything else. I just focus on what I want. The same thing here, except in this case, we have a lot of fractions to deal with. Fractions are more of a challenge, a bit bigger pain. Here we need 1 mole of N2, so we only have half a mole, so we just double that. Here we have an O2, but here we have 2 choices for O2. So which O2 should we use? Well, there it's just a guess. Just pick one and try it. If it works, great. If it doesn't work, try the other one. And so for me, I just go with convenience here. The convenience is this one is double this one. And I get the O2 here. So double this one, and then we have an N2 and an O2. And all we're missing is the NO. We need 2 NOs, so I double this one. And then add those 3, everything should work out. Everything else should cancel. And so Hess's law are just time consuming, but easy, because if you make a mistake, no big deal, you back up and you just try a different equation. Eventually everybody gets it. The problem is on speed, time tests, where then when people, then the people who are fast are going to get the high scores. Well, anyway, this is one with 1, 2, 3, 4, 5, 6, 7. It's not that you're going to add all 7 equations, but you might. And so these are just the standard problems here. So that's Hess's law, but you know, I don't see any equations that add up to this. Do you? I didn't see any equations that, you know, I don't have 7 equations that they're giving me that add up to this. I need something that adds up to this. And so there's one variant of Hess's law that's even easier to use. And this variant of Hess's law is the best. So this is Hess's law 1, let's call it. Hess's law 2 is we add up the equations, but we only add up a specific type of equation. In Hess's law 2, if we restrict ourselves to what are called formation reactions, then it's so easy. Restrict to formations. Okay, well, what does this little f mean? This f means formation of 1 mole of substance. 1 mole of substance from the elements in their most stable state. Under the given conditions. This green is so formation of 1 mole of substance from the elements in the most stable state under the given conditions. This little superscript here means standard thermodynamic conditions. What are standard thermodynamic conditions? Standard thermodynamic conditions are the pressures are 1 atmosphere or 1 bar, and the solutions are at 1 molar. There is no standard temperature. That's because many reactions happen at different temperatures, including room temperature and elevated temperatures. There's no standard temperature in thermodynamics. There's a very common, you know what the most common temperature is? 25 degrees C. And so some people mistake that as standard temperature, but there's no standard temperature. It's just, you know, if you're going to have data, what's the most useful data to have? 0 degrees? Or room temperature? You know, room temperature, for sure. Nobody uses 0 degrees C data. Well, I shouldn't say nobody, because, you know, most people do aqueous chemistry, and it's very hard to do aqueous chemistry at 0 degrees C, you know, because everything's frozen or close to frozen. Now, so when you try to pour a beaker of HCl, you might have ice crystals forming on it. So that's the reason. Anyway, let's go back to this. So if we restrict to delta H of formation, then we don't have to write out the equations. You know, when we add these up, we typically write out the equations and then cross everything out. When we do this, then the delta H of the reaction is equal to the sum of the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants. And then we multiply this by a little nu. This nu is not frequency. This nu is the moles of each, because, you know, delta H is an extensive property, so it depends on how many moles. If you're burning 2 moles, then you get twice as much energy. 3 moles, 3 times. And so we call this nu P for the moles of product, and then over here we have nu R for the moles of reactant. And so this is the equation. Well, this is super easy, because then we don't have to have all these equations, because where do you find a compilation of equations like this? You know, here I have 6 equations, but where do I find a book of equations like this? Well, there are books of equations like this. You know, there are books of equations like, you know, who's collected a lot of thermodynamic data and compiled it into tables. There's a lot of thermodynamic data in what are called JANAF tables, JANAF tables. The JANAF tables are, JANAF, do you know what JANAF stands for? JANAF stands for Joint Army, Navy, Air Force. And they did lots of thermodynamic experiments collecting thermodynamic data. You could look there, but we're going to go to Appendix D. And in Appendix D, we have all these formation reactions here. The first column of data is delta. We read this as standard, it's a little supergroup. Standard enthalpy of formation. That's how this is. Or standard heats of formation. Well, aluminum 0. Why is aluminum 0? Because you look at that, why is aluminum 0? Because it's how we define the reaction that takes place. When we look at delta H of formation, delta H's formation is the formation of 1 mole of substance. So we're forming 1 mole of aluminum from the element in its most stable state. Well, it's going to be aluminum solid. So we're going from aluminum solid to aluminum solid. What's the temperature here? Because there's no standard temperature. We need to figure out what the temperature of this table is. What is the temperature of this table, data table? That's right here. The temperature is 25 degrees C. And so we're forming 1 mole of aluminum at 25 degrees C from 1 mole of aluminum at 25 degrees C. What's the energy change? There's no energy. Kinetic energy didn't change, potential energy didn't change, delta H is 0 for this. Well, this happens to be a formation reaction too, so delta H of formation is 0. Whereas aluminum 3+, take a look at the delta H of formation for aluminum 3+. What is the delta H of formation for aluminum 3+ aqueous? So this is minus 531 kilojoules per mole, right? But let's take a look at some of the data. Let's go to aluminum sulfate. Look at that number on aluminum sulfate. Look at that. That's highly exothermic. Something that's highly exothermic tells me it's very stable relative to the elements. And so let's do delta H of formation for aluminum sulfate. And so aluminum sulfate, we're going to form 1 mole of aluminum sulfate, solid. So if we form that, that's minus 3,441 kilojoules. From what? From the elements in the most stable state. And so we're going to take 2 aluminum solids. Okay, what's the most stable state of sulfur? Well, just elemental sulfur. We need how many of those? 3 sulfurs, solid. Okay, we could use S8, but we'll just use S. Plus, what's the most stable state of oxygen? At 25 degrees C is O2. O2 gas. And we need 12 of those, so we need 6 O2 gas. Okay, and so this is the formation reaction here. We're forming aluminum sulfate from aluminum, sulfur, and oxygen. All these reactions are the same, so we can figure out the equation for each of these delta H's here. But we're going to see something very odd here. And when we look at the data table, and you should always look at data tables, you know, look at the numbers. You know, everything seems to make sense. You know, formation of graphite. What's more stable, graphite or diamond? Well, obviously graphite is, but they're pretty close. So we go on and on. Look at the numbers of these delta H's, and then we see something funny happen. And this is the funny thing that happens, and you wonder, is that a typo or what is that? You know. The formation of hydrogen is obviously it's going to be 0, because if we form H2 gas from H2 gas, is there any energy change? No. The delta H of this is definitely going to be 0. But the strange one is this. If we form H plus aqueous from H2 gas, so to balance this, we'll need half a mole of H2 gas, and then we'll form 1 mole of H plus aqueous. If we form, and this is going to be 1 mole of solution because it's standard. These are all under standard conditions. So we form 1 mole of H plus aqueous from a half a mole of H2 gas. Delta H is 0. And so in order to do this, we have to break the bond, and then we have to ionize it, and then we have to dump it in water. Do you think the energy change is 0? Okay, that's one strange thing. Okay, the next strange thing is, okay, look at this. Look at HCl aqueous. Okay, if we form HCl aqueous, right? What are we forming this from? Well, we're going to take half a mole of H2 gas and add a half a mole of Cl2 gas. Here, we see the delta H of formation standard is equal to 0. Here, delta H is going to be, this is enthalpy of formation standard, is going to be minus 167.2. It's 167.2 kilojoules. Okay. Obviously, this is talked in the book, so most people don't have time to scan this. Okay, now look at the formation of chloride. So we go to a chloride, and so we form chloride, 1 molar chloride solution AQ from the elements, stable state. So 1/2 chlorine gas goes to chloride AQ. What is delta H of formation here? Minus 167.2 kilojoules. And so this is the weird thing here. The weird thing is this, and maybe you could explain what's going on. You know why I'm doing it this way? Normally I just tell you what's going on, but sometimes it doesn't stick, even if I repeat it a bunch of times. So maybe if you figure it out, you can remember it better versus somebody telling you. But the strange thing is this. When we form HCl, AQ, HCl is a strong electrolyte, weak electrolyte, non-electrolyte. It's a strong electrolyte. So HCl is actually H plus AQ plus Cl minus AQ. What's the delta H of formation of H plus AQ from hydrogen gas? 0. So no energy was involved in forming H plus AQ. What's the energy involved forming Cl minus? Well, half of Cl2 goes to Cl minus 167.2. What's the delta H of formation for HCl? 167.2. Do you see something weird or not at all? What's weird? You see something weird. I see something very weird. What's weird is hydrogen, no energy involved. All the energy involved came from the formation of the chloride. Is that possible? Well, maybe it doesn't cost. Let's say if I took some hydrogen gas and tried to form some H plus AQ, maybe there's no energy involved there at all. It just switches back and forth. And so this is weird. Well, it's not weird because I already know the answer. Does anybody know the answer to this? Probably not. The answer to this is this. What happens when you don't know? This we can measure. You take some hydrogen and some chlorine. Boom, it's exothermic. We're going to release that much energy. You do it in you could do this in a bomb calorimeter and figure out what delta H is, right? Releases this much energy. Now the question comes up, how much of the 167.2 came from the H plus, and how much of it came from the chloride? That's the question. But that question is easy to answer or difficult to answer? Well, you say, it's easy to answer. Just get two equations, two unknowns, we figure out simultaneous set of equations. No, what's the other equation? There's no other equation. And so we have two unknowns in one equation. If you have two unknowns in one equation, most people say, no, can't solve it, give up, right? Most people say, if you got two unknowns in two equations, just give up. Don't even try it, right? Because, theory can only get you so far. Theory, you can kind of guesstimate. Well, I guesstimate 50%. How do you like this guesstimation? Half of the energy came from H plus, the other half came from chloride. How accurate do you think my guesstimate is? Do you think it's accurate? No. Well, let me change my guesstimate then. 20% came from H plus, 80% came from chloride. How's that guesstimate? No, that's just random guesses. Well, we can use some theory to figure it out, using some physics or whatever else. But even theory, those have approximations, and those are going to be an error. And so if we don't have anything accurate, then we have two choices. We give up. Because we have two unknowns in one equation, we give up until we can figure it out. Or we do something else. And that something else is because, the chemists, they knew something. Is it possible to form a cation without an anion? Can you just bottle up cations and then, you know what, I don't want the anion, just give me the cation. Can you do that? Like, give me the salt without the sodium. I'll just take the chloride. Is that possible? No, it's impossible. And so whenever you form a cation, you have to form an anion. So somebody came up with a brilliant idea. The brilliant idea is just, hey, let's call H plus 0. Let's just call H plus 0. Well, you know what? That's wrong. That's totally wrong. But they figured out that's going to introduce what we call systematic error. And the systematic error is this. One's always going to be reading too high, the other is always going to be reading too low, but when you add them up, the one that's too high cancels out the one that's too low, and the errors cancel each other out. Does that make sense? And so what we're doing is we're introducing a systematic error here, but you cannot form an anion without a cation. And so if all the cations are reading too high, and all the anions are reading too low, or vice versa, then it's going to cancel out because we form chloride, we've got to form something else. We've got to form a cation. And so if this is too low, the other's too high, and when you add them up, perfect. Right? It's a systematic error that self-cancels. And so this is what we call an arbitrary zero. H plus is defined, the delta H formation of H plus is defined as 0. And so there are three tables within this one table. There are you cannot compare the numbers, right? This makes comparison. This is like, the analogy here is this. What if you had a table, and these are tables of temperature, but they didn't write the units here. And these are Fahrenheit, Celsius, and Kelvin temperatures. Fahrenheit, Celsius, and Kelvin temperatures. And so, where are the units? Why aren't you writing the units? Well, they figure, they figure that you guys are sophisticated enough to figure it out, right? But, I figured that's wrong because, people need more guidance, I think, in this. And so I wish they would have put something here or separated it out or made it more clear because people don't figure it out, was my experience, even though I might tell them a bunch of times. But people don't figure this out. And the problem is this, can you compare chloride with chlorine, these two numbers, directly? No, you can't, because this is like Fahrenheit, this is like Kelvin. You can't compare the two numbers. But can you compare chlorine with chlorine trifluoride? Yes, you can, because those are like 2 Kelvin numbers. Well, why aren't they telling you this? Why aren't they telling you this? Because they did tell you this. They told you inside the text, you know, not so directly, but they tell you. And then they ask you to figure it out. But, you know, usually you have to tell them over and over and over again until it clicks. And so they only say it once in passing. Most people just pass it by, right? And so the numbers are very tricky because the cations are relative to an arbitrary 0. What's a 0 point in cations? What's a 0 point for the cations? What's 0 kilojoules for cations? For cations, the 0 point is defined as H plus formation. What's a 0 point for anions? There's no 0 point defined for anions because anions were based on the cation, and the anion is based on the chloride being minus 167.2. Okay. What's a 0 point for everything else? The 0 point for everything else are the elements in their standard state. And so we got 3 different sets of numbers in this one column here. And so you have to keep track of it. The cations can be compared to the cations, the anions can be compared to the anions, and everything else can be compared to everything else, but you cannot cross-compare because that would be like saying, you know, which is a higher temperature, 100 or 300, you know? And you're going 100 versus 300, 300 is the higher temperature. No, I meant 100 Celsius versus 300 Kelvin. Oh, 100 Celsius is a higher temperature. But I'm not going to say the units because I expect you to know. Okay? And so is that clear? Well, you know, that's confusing. I don't want to deal with this. But unfortunately, the same thing repeats. From this column to this column to this column. Right? And so we have to be aware of that. All right, once you're aware of that, then using these numbers is so simple. You know, when I didn't know this. You know, I didn't know this when I took general chemistry. You know, I was good at doing these calculations, these delta H formation calculations, because I just read the number off here, plug it in the equation, and calculate the answer. But when somebody started asking me about what those energies refer to, then I had no clue. You know. No clue. And so using delta H formation is easy, but knowing what the numbers mean is quite a bit different. And there are many famous quotes saying that, you know, the hard part in science is not the calculation. The hard part in science is knowing what the numbers mean. And so let's figure this out. Now, with that said, we can just do this calculation quite easy. C6H12O6 solid. Let me just rewrite it here. This could yield 6CO2. So we want to figure out what delta H is. Well, delta H for this reaction, what's the easiest? Should I do constant pressure calorimetry? No. Should I do constant volume calorimetry? No, because it doesn't take too much time. Should I do Hess's Law 1? No, I'm going to do Hess's Law 2. Hess's Law 2 by far is the easiest way to figure out what delta H of reactions are. And so doing Hess's Law 2, that's going to be easy as long as I have the data. And Appendix D is pretty thorough, so let's just take a look. Delta H of the reaction is going to be the sum of the delta H's formation of the product. So 6 moles of CO2 times the delta H formation of CO2 gas, the states matter, plus 6 moles of H2O liquid, times the delta H of formation of H2O liquid. Okay, that's my products, right? Minus the reactants. So I have 1 mole of glucose. I'm going to write it out, gluc. times the delta H formation of glucose plus 6 moles of O2 times the delta H formation of O2. One of these you should have memorized. Which one? Which delta H formation do you know right off? Normally I don't give this on a test because you should know it. Which delta H formation should you know? This one. What's the delta H formation of O2 gas from O2 gas? We're forming 1 mole of O2 gas from 1 mole of O2 gas at 25 degrees C. The delta H formation is 0. So that term is 0. The others we have to look up. And so let's just look them up. When we look it up, CO2, so we go with carbon, and we find CO2. Delta H formation of CO2 gas is here, it's minus 393.5. Minus 393.5 kilojoules per mole. And we got 6 moles, so we go to multiply with 6. Then we go to H2O liquid, so we go to hydrogen. Hydrogen is H, so this is alphabetical. P, no, it's not alphabetical, is it? LM, oh, it is alphabetical. HI, it's past it, ABC. Oh, here it is, hydrogen. So we go to water. H2O liquid is minus 285.8. H2O gas is minus 241.8. There's 44 kilojoules of difference between liquid and gas. We're going to liquid, so it's minus 285.8. Minus 285.8 kilojoules per mole. And then glucose. Glucose would be carbon, but this table's divided. When you look at the table, let's go on here. At the end of this table, they have some organics. Glucose is an organic, so let's look for the organic substances here. The methane, acetylene, ethylene, ethane, propane, butane, benzene, cyclohexane, naphthalene, formaldehyde, acetaldehyde, methanol, ethanol, acetone, acetic acid. Does acetic acid burn? Well, these aren't combustion reactions, they're just formation. Acetic acid does burn. Benzoic acid, methylamine, and yeah, you know what? Glucose is not here. Glucose is not here. Let's go back to the problem. They give us. You see, they gave us delta H of formation. Standard enthalpy of formation of glucose solid is minus 1273.3 kilojoules per mole. We go here, minus 1273.3 kilojoules per mole. Okay, so what does that equal? You can just calculate that out. Figure out what delta H of the reaction is. Okay, once we have delta H of reaction, that gives us the heat of reaction for 1 mole of glucose. Will 1 mole of glucose be enough to climb the mountain? Well, let's see. And so this is an advanced problem because they don't tell us how much energy is required here. Directly, they tell us indirectly. Calculate the mass of glucose metabolized by 58.0 kilogram person in climbing the mountain. Assume that the work performed in the climb is about 4 times that required to simply lift a 58.0 kilogram mass by 1,450 meters. Okay, so we're going to assume this, that the work required to climb the mountain is equal to 4 times raising a mass. Well, 4 times raising the mass, this is going to come from physics, MGH. And so they didn't give this to us from physics. It's how much energy it takes to raise a mass, you know, of a certain mass against gravity, a certain height. And so we're just going to assume it. And so 4 times the mass is 58.0 kilograms. That's how much the person weighs. And so if you were to lift a mass 1,450 meters, this is the amount of energy. So the person's climbing the mountain, so we're just going to quadruple it. Times g, which is 9.8 meters per second squared. What is g? Does anybody know g to 3 sig figs? What is g to 3 sig figs?
0.
Is it 9.80? 9.80 meters per second squared times the height of 1,450 meters. And so we get kilogram meter squared per second squared, which is joules. And we're going to quadruple it. And so what does this come out to? Well, this is going to be the energy required to climb. To make the climb. How much energy is that? I'm just going to calculate it. And so this is equal to 4 times 58 times 9.8 times 1450. It's a lot. Make a mistake. No, I guess that's right. 3,296,720. 3,296,720. Joules. Or in other words, 3,296 kilojoules. So we need 3,296 kilojoules. Did anybody calculate this?
I had negative 2.2802.
2802.5 kilojoules. You know, a mole of glucose is almost enough. A mole of glucose is about 200 grams, 190 grams. It's almost enough. 190 grams, that's a lot of sugar. 200 grams of sugar is a lot. But we're going to need more than a mole of glucose, huh? Actually, we're going to need a bit more, because that's assuming that glucose gets converted into work with 100% efficiency. Unfortunately, the glucose does not get converted into work with 100% efficiency. And so this is the amount that we need. So we have to do a dimensional analysis problem using 70% efficiency. What is 70% efficiency mean? And so this is what we're going to do. The fixed amount is this. We must have 3,296 kilojoules. Otherwise, we don't have enough energy to make the climb. And so this is our given here. But there's only 70% efficiency. So actually, if there's only 70%, let's say, you know, if you must have $3,000, but you know you're going to lose 30%, then you're going to have to compensate for that. And so what that means is this: for every 70 kilojoules that are yielded, in theory, we have to have, this is our actual yield, we'll have to produce 100 kilojoules, right? And so how should we do, what should we call the 100 kilojoules? For every 100 kilojoules produced, we only get an actual yield of 70 kilojoules. Does that make sense? That's 70% efficiency. And so that means we need more. You know? We need 100, we need this much more glucose. 10/7 more.
Multiply the 3,000 number by 1.3 is really what you need.
Okay. That would be good. I'll just leave it like this. Huh? Okay, and then this. We know that there are going to be 2,000, I just erased it, sorry. Can you repeat that? 2802.5 kilojoules. Now it's negative, but I'm not going to write negative because I'm just going to say this much produced. Produced means, you know, it's exothermic. Because I don't want negative grams. So 2,802.5 kilojoules produced for every mole of glucose burned. And then we need to calculate the molar mass of glucose. The molar mass of glucose is 6 times 1201, 60, 7206. And then 12, 101, 1212. 6 oxygens, 1600, 60, 96, 18, 10, 180. All right, 180.18. Let's make sure I did that right. 180.18. So 180.18 grams of glucose per mole. And so that would be the mass of glucose required to make the climb. A little over, maybe around 200 grams. 200 grams of glucose. 200 grams, you know, glucose is maybe slightly more dense than water. And so, you know, you're looking at almost 200 milliliters of glucose. Something like that. Sugar. All right, so that's the easiest. And once we have the delta H's, then we could use the delta H's to make all kinds of predictions with reactions. And so this is pretty much all of the chapter. You know, the rest of the problems are using delta H's as conversion factors. So we do that. And we use this, you know, delta H is a conversion factor. A conversion factor we use in dimensional analysis. So we get 2802.5 kilojoules, you know, for every, minus 2802 for every 6 moles of O2 consumed, etc. And so we could figure out the relationship with any of the species in the table. All right, let's stop here and then